Hello and welcome in my another episode of my tutorial series on STM32 programming. Today I want to show you how to generate a PWM signal. This time I would like to show you two codes. In the first code I will show you a simple PWM generation. I will generate two PWMs. Both of them will be edge aligned. In the second code I will go a little bit deeper and I will show you how to generate simultaneously two PWM signals in which both of them will be phase shifted. So let's go. Again, I will no longer write the codes in a real time because I make mistakes and this is not good for the tutorials. So I will explain it to you line by line what I'm doing. So the first line, include main.h, this is generated by CubeMX. These are the libraries which you should already know if you watch previous episode. I wrote all three of them. MCU clock 48 MHz, important to know, especially when we are working with the timers. Here I set up the pin ports and pins for our application. So I have LED pin 10 or GPIO B, then pin 9 on port A and pin 8 on port A. Pin 0 for GPIO A. You may ask, why do I have ADC in there? Well, I will go a little bit deeper because I want to change not the duty cycle, but I want to change the frequency according to the turning of the potentiometer. Next is variables. This is very simple. I use just one. I call it a ticker and it will toggle itself between 1 and 0 depending on the interrupt. And here I will click over here. Sysdig config, again, for properly set up the system timer, so our delay function will work in milliseconds. MCU clock divided by 1000, okay. Then I set up the ADC pin as analog input. I set up analog output for LED, an alternate function for PWM ports. I call it low and high, but you can call it however you want it. Below that, we can see that I am selecting the alternate function. As we know, the timer is a peripheral and we need to set up for the GPIO the alternate function. For timer 1, you can see in the datasheet that the timer 1 is in alternate function 6, but also in another alternate function, but because I'm using pins 8 and pins 9, I want to use channel 1 and channel 2. And both of them are alternate function 6. So we can see that I'm moving bitwise 6 on the positions in the alternate function register. Again, if you watch previous episode, you should already know that, but I will show you still. We'll go to the reference manual, GPIO, registers, alternate function. We are in a higher one. And I'm using pin 8 and pin 9. Therefore, for pin 8, I can just write bitwise 6, which is 0, 1, 1, 0. And I don't need to left shift it. For the pin 9, I actually have to left shift it for by 4 positions on position 4. So I have 0, 1, 1, 0. Then let's go further. This is all for the GPIO initialization. Now let's go for the timer itself. At first, enable peripheral clock. Again, I will show you where it is. We'll go into reset and clock control, RCC registers. And it's, yeah, APB2 peripheral clock enable register. And on bit 11, we can see timer 1 enabled. This will enable the clock for our peripheral. Next, we set the prescaler. I don't want to generate the PWM signal at the maximum frequency of the core. You want to use whatever frequency you want. You want 50 Hz, 50 kHz, 250 kHz. This time, I will preset it in a setup for 250 kHz, which means we have clock frequency 48 MHz. I set prescaler 3, but actually it doesn't divide the frequency by 3, because when I will show you in the reference manual, timer 1, functional description, and it is prescaler. Where should I find you? Actually, I think I can go straight to the registers. But it is definitely somewhere else, but it will be more simple to find it inside the register. Here, prescaler. And here you can see the equation. This is the clock. We have 40 MHz here. And this is the value prescaler, which is this register, 16-bit register, and it's +1. So the reason I'm setting prescaler 3 is that I know that there is already +1. So I divide, we have 14 MHz, I divide it by 4. We have now 12 MHz. Okay. Then I select the ARR, which is auto reload register. It should be over here. And I will actually show you also how the PWM generation works with the ARR function description, PWM mode, and I actually use the simple PWM mode. Oh yeah, this is it. H-line waveform, this is what I use. This is, for example, for ARR8. And as you can see, if you set ARR8, it actually counts from 0. It doesn't count from 1. So actually you have 9 ticks before one period is done. So you have to also take it in mind. So here I'm setting AR47, but again, in reality, basically it's 48. So now we have 12 MHz. And if I divide 12 MHz by 48, I actually have 250 kHz. This is what I want. Actually, I haven't told you before, I want to change the frequency between 50 kHz and 250 kHz. Right now, I'm setting it for 250 kHz, and then by potentiometer, I will change it from 250 kHz to 50 kHz. But you can set it whatever you want. The next is capture compare. I will go. Actually, I can explain how capture compare works. So you have, for example, your ARR8, and you set your capture compare 4. So the timer counts 0, 1, 2, 3, and now starts the 4th tick. And it, for example, either resets or actually it sets the PWM. Depends what PWM mode you use. I will explain it later. So, for example, for 8, again, you can see that if you set CCR8, it actually doesn't do 100% of duty cycle. It will do not 90%, like 87.5, something like that, because they have 9 and not 10. So you can see that you have to select the capture compare register larger than your ARR if you want 100% duty cycle. So it bigger than 8. Theoretically, you can set like 10, 20, but it's better just to set it, for example, to 9. And I set the capture compare 24, so I want actually to have 50% duty cycle, because ARR is technically 48, but I wrote 47. And then there will be 24 ticks before the PWM falls to 0. So I will have 50% duty cycle. Now let's go to another register, CCMR. This one is actually more important. As you can see, if this is your first tutorial series you ever watch for programming, this register doesn't look very friendly, but it is actually quite simple. Basically, everything with I at first is for input, everything with O is for output. And I want to generate PWM, I want to output a PWM signal, so basically only these upper things interests me right now. Now we'll go a little bit lower. At first you have to set up your OC1M or OCXM. What it is, let's take a look. It's your output compare mode. You know, the timer can work in so many modes. And I want to use a PWM mode, and I want to use for one channel PWM mode 1 and for another PWM mode, so you can see the difference how it works. So PWM mode 1 in upcounting, which is what we have. I can show you over here. Here is in control register 1, here is pin direction, and it shows you if it's up counter or down counter. I'm using up counter this time, just to make it clear. So again, let's go down. PWM mode 1. In upcounting, channel 1 is active as long as the timer counter is lower than capture compare register, else is inactive. So it means that if our period starts, at first we are in logical 1, and then in a certain moment we will fall into logical 0. And in PWM mode 2, it is in upcounting regime, the channel 1 is actually inactive as long as the counter is smaller than capture compare register value. So it's actually the opposite. And we can see over here that for mode 1, it is 0, 1, 1, 0. So I'm setting first bit, second bit, and third bit and zeroth bit I leave at 0. Then for the second channel, which is CCMR1 also, I set up second bit, first bit, and zeroth bit. Why? Again, reference manual. 0, first and second bit is 1, third bit is 0. But then there is this PE. What is it? Again, I will. Is it above it? A little lower. Here, preload enable. This is quite useful if you want to set your timer, if you want to preset your values basically in the timer. So during your setup, your timer will actually generate something without going into the infinite loop, the while loop. Or if you do not want to wait for an interrupt or something like that, you actually can preload some values into the timer. So I'm setting it to 1. Here you can read that timer 1 CCR preload value is loaded into active register at each update event. So if I did not have done, if I wouldn't set the preload bit to 1, I actually, this what I've done doesn't make any sense because it actually doesn't load itself. I can set the prescaler, I can set the auto reload register, but this actually it wouldn't basically exist if I would write it like that, and I wouldn't set the preload enable. Then, and I do the preload enable for both channels. CCER, next register, capture compare enable register. I'm actually setting C1E enable, yeah, capture compare output enable. I set it to 1 and I have it configured as an output. So the signal is output on the corresponding output bit depending on MOVI, OSSE, OSSR, etc. etc. So if I wouldn't have set this bit, the PWM would be generated, but it actually couldn't get outside of the microcontroller. It actually, the PWM would be generated, but it doesn't get outside the MCU, basically. Your pin would look dead or inactive if you wouldn't have set it up. So I set it for both channel 1 and 2. Next is BDTR. Let's find it out where it is. Here. And I set up the MOVI bit. Yeah, MOVI. And I'll be actually honest that even if I set it or doesn't set it, the function is more or less the same. I can read it for you that this bit is cleared asynchronously by hardware as soon as one of the break inputs is active. It is set by software or automatically depending by AOV bit. It is acting only on the channels which are configured as an output. So I think basically this is like for the first conversion, the first generation, and if it's okay, it actually, the hardware will clear it. So I just set it in a software to help it start up, to make the first generation good. Actually, as I said, like sometimes I do not write it, and the code actually works without it. But in a ST literature, I read that actually you have to set this bit, so I'm setting it up. But again, as I'm saying, from my practice with it, it didn't do like any sort of errors if you did not set it. Next is, yeah, control register 1, and I'm setting CEN bit. CEN bit is the least significant bit. Counter enable. What else to say? Counter enable. And EGR. Surely, yeah, it's... did I overlooked it? Event generation register, yes. And I'm setting UG. Update generation. As you can read, reinitialize the counter and generates an update of the registers. Note that the prescaler counter is cleared too. Again, this is actually important to do. And do not skip this bit. So this is all for the timer configuration, or let's say timer which generates the PWM. And now basic routine, I set up the ADC. You can see it in my library. What did this function do? Timer fitting configuration is also in the library, so you can see what it does. ADC start conversion. Okay. let's go into interrupt. I generate an interrupt 10 times each second, and I do like I toggle the LEDs to make sure that the program works and it actually does something. Then I set the ticker value to 1, and I will read the converted value from the ADC data register. So I can read the value at which the potentiometer is set to set the frequency of the PWMs. Then let's go inside the while function. If ticker is equal to 1, which means that the interrupt has occurred, then we have new value from the data register of the ADC. Timer 1 auto reload register equals converted value multiplied by 192, for example, divided by 4095 plus 47. Basically, let's say if our converted value is maximum, which means 4095, this will basically we can exclude, we can throw this away because it will be 1, and we have 195 plus 47, 192, sorry. This is 239 plus 1, and if you divide it or multiply by 4, you have 50 kilohertz. So if I will turn the potentiometer all the way to the max, I will have 50 kilohertz, and if I will keep it 0, I will have ARR, this will be 0. I will have ARR 47, which is how it is set up by the initial setup. But then I also need to recalculate the capture compare register, because if I do not change the capture compare register value, then basically with the changing frequency, I will have also changing duty cycle. But because I want 50% duty cycle all the time, I will take the ARR, and actually this can be, you have to do it like this. Why? Because we already know that auto reload register value is actually by 1 smaller than in reality it is. So to have 100% duty cycle, you actually need to have the capture compare register value by 1 larger than the ARR. So now we have the correct 50% duty cycle. So I will now record you the results, and I will move on the next code. Let's go into our second code. Again, this is the same. This is the same. But if you see that I'm actually using 4 pins for one timer, but I want to do the output just from 2 of them. You actually do not have to set the GPIOs for those 2 pins, but just to make it more visible, I will do it. Again, the goal of this code is to make 2 phase-shifted PWM signals. And to do so, let's go functional description, combined PWM mode. And I will actually at first show you the picture, how it works. Because sometimes you want to create more complex PWM signals for whatever application, I don't know. And here you can see that the result or the output signal is the combination of logical AND of these two. For example, so we can see that the OC1 ref, here it begins at 0, then it goes, for example, in like 10% to 1, and it stays on 1 and goes down. And the OC2 ref starts at 1, then falls to 0, and stays 0. Because it is AND, we can see that the result is this. So let's say like we have phase shifted, for example, like 20 degrees phase shifted PWM signal with the duty cycle of like 25%, let's say. Or we can use another combination, which is OR method. So again, for example, our signal starts at 1, and in the end, it falls to 0, and then it resets itself to 1. And the second signal starts at 0. At, let's say, like 85%, it goes to 1 and stays 1 until the outer of the register will reset itself to 0. And the result signal is 1, 1, 1, 1, 1. Let's say on 75% it falls to 0. This is like duty cycle. It's actually not duty cycle because it's 0, but it's like 10% of the period, let's say, and then it goes to 1. Basically, if you want your output signal to be in during one period, 0, 1, and 0, you use AND. Then if you want your output signal to be 1, 0, 1, basically, let's say you want to make holes inside the continuous signal, then you use OR. And the reason is this. I will actually read some of it. So you can see you can generate two edge-aligned or center-aligned PWM signals. You can program the delay, phase shifts. The frequency is determined by outer rear of the register. The duty cycle and delays are determined by the capture compare registers and by the two of them. And the resulting signal is made by of an OR or AND logical combination of the two reference PWM signals. So you can see that OC1 or OC2 is controlled by capture compare register 1 and 2, and output compare 3 or 4 is controlled by the channel or the capture compare register 3 and 4. And yeah, combined PWM mode can be selected independently on two channels, one per pair, by writing 1100 or 1101. Depends if you want combined PWM mode 1 or combined PWM mode 2. I will show you in the registers what it is, what's the difference. And the important thing is, when a given channel is used as combined PWM channel, its complementary channel must be configured in the opposite PWM mode. So let's say when I'm using combined PWM mode 1, the other must be combined PWM mode 2. I will put it more simple. And actually this is quite nice. Basically, you want to configure your channel as a combined PWM mode 2. Again, I will show in the register what the mode 2 does. And channel 2 must be then configured in PWM mode 1. If you want to use combined PWM mode 1, you must use PWM mode 2. And we already know what PWM mode 2 or 1 does, but again, let's go into the registers. It's over here. And here are the combined PWM modes. Combined PWM mode 1 has the same behavior as PWM mode 1. And the output compare signal is the combination of, or is the logical OR between OC1 and OC2 ref. So this means that, for example, PWM mode 1 works as a PWM mode 1 like in general. So it is active as long as the counter is smaller than capture compare register. And the other channel, which is a referential, must be in PWM mode 2. Which means that it is inactive as long as the counter, or as long as counter is smaller than capture compare register 1, the channel is inactive, and then it's active. And I can show you again on the picture, which is right here. So for example, for OR, we know that they are using the first channel must be in combined PWM channel mode 1, and the second must be PWM mode 2. So this is PWM mode 1. At first it's 1. And this is PWM mode 2. It is at first 0. And then it's 1. The reason why you cannot use two same PWM modes is very simple. What should happen? You would have this one. And the second channel would be, for example, 1, 0. And as you see, it's OR. So the resulting signal would be basically this signal. Because this will be 1 always, and even though this will be 1 and 0, it doesn't have any effect on this signal. So you must use the opposite PWM modes to actually have a different result, to make some sort of phase shifted PWM signal. And the same works for the mode 2. The mode 2 actually, the combined PWM channel mode 2 works as the PWM mode 2, so the other channel must work in PWM mode 1. And here we can see it. This is combined PWM channel 1, basically first referential channel. At first it's 0, then it's 1. And this is mode 2, mode 1. At first it's 1, and then it's 0. And this is 2. I will again show you in the registers. Mode 2 here. Yeah, the same behavior as PWM mode 2. It is a logical AND between output compare 1 and output compare 2. In this application, I will use this value, this mode, because I want to my signal basically look like 0, 1, 0. Not 1, 0, 1. So let's take a look into the code. We can skip this. We can skip this. We can skip this. Again, I'm setting them as an output, but you can set for GPIO output basically only the two channels you actually want to get output from. But for example, if you want to control how does the referential PWM signals looks like, and compare it with the output signal, you can do it if you send it as an output. Again, I showed you how it works. Only one little information, that the channel 4 for timer 2 is alternate function 11. So again, you must find it in the datasheet if you want to use different channels, different timers, what alternate function it actually is for a certain pin on a certain port. 11. So again, we are setting the peripheral clock, we already know that. And these two are channel, this is channel 1, this is channel 2, this is channel 3, and this is channel 4. For channel 1, I want to set the combined PWM mode 2, which means 3, 2, the third, second, and 0 bit will be 1. Let's take a look into the reference manual. 1101 combined PWM mode 2. And actually it is the same for the third channel. These two are the same because I'm using AND. That the result PWM will be combination of the AND of the signals. And the channel 2 will be set in PWM mode 1, which is 0111. Actually, sorry, this one is PWM mode 1, 0110, right. So it's second and first bit, and then preload enable. Over here is the same preload enable, and you set first and second bit. The least significant bit and the most significant bit of these 4 bits, you leave at 0. Then, again, I want to change the frequency from 250 kHz to 50 kHz. Right now in the setup, in the main, I'm setting it for 250 kHz. Prescaler 4, 3 plus 1, we know that. ARR 47 plus 1, we know that. The result frequency will be 250 kHz. And now I'm setting the capture compare values. And I want, for example, my first signal, actually both of them, I want them 40% duty cycle. And I want it to be 5% shifted. So the first 5% of the signal will be 0, then it will go 1 until the last 45%, then it go to 0. And this is for the first combined PWM channel. For the second combined PWM channel, I will set up that after 50% of the period will last, then 5% will be 0, then it will go to 1, and it will go to 0, the signal will go to 0 again at the 95%. You will see how it looks like on the oscilloscope. It is quite hard to explain it like this. Then I'm setting again in, yeah, and important note is that this CCMR capture compare mode register, the other two channels are in register 2. So this is different. This is the same, CCER. Again, I will show it to you. Enable register, and I want to enable the output only for the channel 1 and channel 3, because these two are the combined PWM mode. This is where the PWMs will mix themselves and we get the result. Again, BDTR, the ST documentation said you should set it, I set it. Peripheral, okay, and this is update generation, I set it also. This is the same. This is the same as the previous code. The difference is over here. I'll click on this. This is the same. The datasheet told us that the ARR defines the frequency. And again, we are recalculating the capture compare register values. With taking into account the change of the value inside the ARR register. So this is how it is, and I will show you the result on the oscilloscope. As you could see on the video, the PWM is actually not clear, and both of them have the same issue, that there are some sort of small spikes where the signal actually should be 0, there are spikes when the other PWM signal goes from 1 to 0. To be absolutely honest, I don't know what causes it. As you could see, the code is actually quite simple. Maybe it is an hardware issue, which I hope it's not, because these spikes are actually quite irritating. Because, for example, I use this PWM for driving MOSFETs, for the MOSFET drivers, and the MOSFET driver is actually so sensitive that it actually detects these small spikes, and it actually sets the MOSFET on for a very short period of time. And you also like you can use in a hardware or in a breadboard small capacitor to get rid of these spikes, but actually you will get slower on, so you will get larger dead time between 0 and 1 in your main PWM signal. The PWM signal is the most important signal you can basically generate from your MCU. You can use it for driving servos, motors, or, as I said before, MOSFET drivers, etc. So it is very good and very important to get very well familiar with them. I just showed you 2 ways how to generate a PWM. One is simple edge aligned generation, and then I used a combined PWM, which is more, let's say, complex. But if you want to generate more complex PWM signal, you can also use it very well. I just want to show you, like, this is the edge align mode. You can use center align mode. Then you have asymmetric PWM mode. This is the combined PWM mode, which I showed you. Combined 3-phase PWM mode. This is when you really need to create some sort of complex things. Oh yeah, that's more or less for it. There is also 6-step PWM generation. I will not go into that right now. This was all for today. I hope it wasn't too rushed, but I really want to move on more complex subjects, and I want to move out from the basics, so I can show you how to interact with more modules, how to control servos, etc., how to make your own projects. So this is why I'm rushing it a little bit, but as I said, I hope I explained everything. You can write me a comment. Thank you for watching. I appreciate your support. If you want to, you can share my videos with another hackers, however you want to, and see you in the next episode. Goodbye.